Welcome back. This is segment 2 of section 4.2. As you recall, we were talking about in the first segment, we were talking about translations and how to take an equation that has a non-negative C or D value and produce the graph from it. And as promised, the next and actually hardest process that we do in this chapter is to take a graph and produce the equation of that graph. And so I'm going to try to do that by way of example. I'm going to try to give some indications of how that might be done. But let's, and I'm starting on page 4, which was, I kind of had half a page left. I don't want to have too much blank space on my sheets, but we'll kick it over here and we'll get started with some sort of relatively simple examples, and we'll build up some that are a little more complicated. So first off, when we're dealing with a graph, when you have a graph and you want to produce the equation, the process is to first you want to identify the location of the, and I don't really have, this is not a technical term, but the regular or standard origin. And what I mean by that is that on sine and cosine, there is a specific point that sort of from a graphical perspective that the normal, if we were just talking about y equals say sine of x or cosine of x, the origin would correspond with that. So for example, in this graph that we did before, this was cosine, but remember that cosine starts with a peak, but the origin is actually down here, right? So if we were to find this point right there, then this kind of, that point, what the normal origin would be, tells us what both the C and the D value is. Okay, so I'm gonna say kind of in parentheses here, to determine C and D. And then the second task is to determine the period. Again, this is just by looking at the graph, and we'll use the equation. Remember that equation to find B, if you had the period, was B equal T naught over P. So from the graph, you determine what the period is, and you divide that into what the normal period is for the function in question. And note, for both sine and cosine, it's 2 pi. It turns out that it's different for some of the other trig functions. And then finally, and this, I'm gonna use this, I'm not gonna use the word amplitude, but you will finally determine A by, well, with sine and cosine, you just simply look at the difference between the high and low, but maybe I'll just say graphical means, and I'll kind of talk about what that means for each different function. So let's take an example. Section 4.2, now we're on page number 5. So let's look at this equation. So I've got one that I sort of prepared here. So here's my X and Y axis, and I'm gonna kind of use some tools here. Put this line in place so I can not make something that looks too terribly bad. And okay, so I'm going to put some labels on here, and we can kind of work. I'll do one where it's very definite what we have going on here. But I'll say that this point is, let's make this 5 pi over 3. And we'll make this point over here negative pi over 3. So this is half a period, right? Because we go from a high to a low. But if we repeat the process, it looks like 6/3. So this point would be 11 pi over 3. And I think that's enough to be able to determine the equation of either sine or cosine. And then I'll put some labels here. Let's say that this is, let's make this 1, and this one down here, -7. Okay, so now this equation, this graph has every kind of transformation and translation that we've talked about. It is there, the A, B, C, and D value, they're all different. So what we want to do is first, let's do this. Usually the instructions are that you will be told what kind of function it is, either sine, because sine and cosine look identical. I mean, there's a little shift to them. But we'll just say this is a sine function. Okay, so following that step by step, notice that this point right here corresponds to what the quote normal origin or standard origin of the sine function would be. So if we find the coordinate of that point, this is C comma D. Okay. Now we could also say that this is C comma D, because remember, sine is a periodic function, which means that you can have different values of C and still have the right equation. So we're going to generate an equation for this graph. We could have others, obviously. We could also, throw in something dumb like put a reflection or something like that, but we're looking at sort of the simplest solution. So what we would like to do is find out what the coordinate of this point is. Notice that this is halfway between this high and low. So if we take the average of these two, which is 2/3 pi, that will be our 2 pi over 3. That will be our C value. And for the D value, we take the average of the high and the low. That will actually be -3. So our C value is 2 pi over 3. Our D value is -3. And I'm just going to go ahead and write that down right here, just like this. C comma D equal to 2 pi over 3, comma, -3. Okay, now we arrived at that simply by figuring out where the standard origin is located, what the coordinate of the standard origin of the sine function is at. Now going to the B value, notice that from point to point, from say any feature you want will tell you what the period is. So this distance is P from corresponding low points. You could also do it with high points, but we don't actually have the coordinate, the position calculated here. You're going to get the same value, but whatever, this is more convenient. So if we take the difference between these two, so 11 pi over 3 minus a -pi over 3 turns out to be 12 pi over 3, which reduces down to 4 pi. So the period is 4 pi. So B is equal to the normal period for sine, which is 2 pi, divided by the actual period, which is 4 pi. So this is 1/2. Okay, so now we have the B, C, and D. The last thing to do is to find A. And like I said, we intentionally did not put a reflection in here, though you could, but that's just unnecessarily complicated. So the A value is the difference between the baseline and the high point, at least on the sine and cosine function. So you'd have to go up 1, 2, 3, 4 units to get from -3 to 1. So that's our A value. A is equal to 4. And maybe I'll draw it over here because it works the same on this side as well. You could look from the baseline to the bottom. This is actually the absolute value of A. You determine whether it's positive or negative based on whether it's reflected. But as I said, generally speaking, for sine and cosine, there's no need to use reflections. You'll pretty much always have a positive A value, and you use the C value to get rid of that. Now that's not necessarily true with tangent, and that's kind of the next one that we'll look at in section 4.3. So if we were to now write the equation, y is equal to the A value, which is 4, times the function sine of the B value, which is 1/2, times x minus the C value, which is 2 pi over 3. Close off all the parentheses, minus 3. And that is the equation of this graph. Okay, this one was, by comparison, this one was relatively easy because it really didn't require any interpretation. Normally speaking, when you're trying to write the equation of a graph, the only trig functions that I am aware of any practical use for are actually sine and cosine. Now the textbook will take us into graphing, taking the graphs of tangent, cotangent, secant, and cosecant, and generating these equations from them. But from a practical standpoint, that's really not done very often. However, there are lots of physical phenomena that either are sinusoidal, and they have this basic shape, or they look a lot like that. Like this isn't, I'm sure all of you have seen like a heart meter, the little beep, beep thing that you see sometimes in movies, or maybe you've seen them in real life. You know that doesn't look like this. This doesn't have this shape, but it's kind of like this. It looks a little bit like it, and you can use some of the features of that graph to write an approximate equation for the phenomena. There's a couple of example problems in this section, I believe, that do just that. And so just be on the lookout for them, because it's not always going to be something that's exactly sinusoidal. It'll just kind of look like a sine curve. So let me do one more problem where it's not so obvious what the equation is, and it does require a little bit of sort of interpretation. So let me start by, this is section 4.2, page 5 now, page 6 now. And so I'm just going to draw a graph. So let me kind of start here. Kind of tilting here a little bit. And then I'm going to put a coordinate axis on here. And just to make it interesting, I'm going to make this not in the middle is 5. Not in the middle is 10. And then I'll put some units out here somewhere. Let me make this, let's make this 10. And maybe, let me see here. I'll kind of maybe put 20 out here somewhere, maybe where we can't actually tell it. Okay, so what do we do with this thing, right? How do we make sense out of this? Well, the best way to create a graph of this thing is to start by trying to figure out the coordinates of some of the primary features, the principal features. So looking at this, looking at these coordinate axes, if we can figure out what the equation of this point is, and maybe this point and this point, we don't necessarily need both x and y, but if we have the coordinates of those points, we have enough to be able to determine the equation. So let's use this axis first to determine the x coordinate. So I would say that this is close enough to 10 for us to call that maybe 10. And looking back at this point, that's a little bit more. It's not 0, so maybe it's 2 or 3. So let's call it 2, because I think it's a little bit less than 3. And now this point in between them has to be halfway. So this will actually have an x coordinate of 6. Now let's look at the y coordinate. So I'd say that this is probably a little bit closer to 10 than it is to 5, but it really kind of looks like it's about in the middle. So I'll make that 7.5. It's kind of maybe more significant digits than this is worth. But down here, this looks like this might be 3, somewhere around 3. And of course, 10, that's another maximum, so it has to have the same x, it has to have the same y value, 7.5. Okay, so with those 3 points, we should have enough to determine A, B, C, and D. So first off, note that A, well, let's say this is to make it simple, let's make this a cosine function. So this is a cosine function. We did a sine last time, so this seems appropriate. Okay, so for cosine, remember that the cosine at x equals 0 is a maximum. And so what we need to do is we need to find where the origin would be relative to the first maximum. And so that's actually a point halfway between them. It's kind of like right there. That's the point that we want the coordinates of. Now, its x coordinate is equal to the x coordinate of this maximum, but its y coordinate is actually somewhere between these two. In fact, it's halfway between. So this is 2, and the average of these two is 5.25. And remember, the standard origin, the coordinates of the standard origin and the shifted coordinate axis is the C and the D value. So from the graph, we get that C comma D is equal to 2 comma 5.25. Okay, the B value is based on the period. Now, if you notice, between these 2 points, this is a complete period. So the distance between them is actually 10 minus 2 equals 8. So the period P is equal to 8. So the B value is equal to the normal period, which is 2 pi, divided by the actual period, which is 8. And it turns out we get a B value that's got a pi in it. So this will be pi over 4. Okay, kind of a weird sort of value, but whatever, it's all the same. And then finally, the A value, remember that's going to be the difference between the Y value of the baseline, which happens to be this D value, and the maximum. So this looks like the distance is 2.25. So that's going to be our A value. And if it had units, you know, that's how things really should be. If you're looking at an application, this could be like, oh, I don't know, maybe watts per square meter. If you're looking at like a, you know, an oscillating, I don't know, whatever. And maybe this is a certain amount of time, so 10 seconds or 10 years or whatever else. These things would have units, but as mathematicians, we don't really care too much about units. That's more for a physics class. So anyways, now that we have A, B, C, and D, it's going to be relatively easy to write this equation. That y is equal to the A value, which is 2.25 times the function, which remember it said it was a cosine function, of the B value, pi over 4, times x minus the C value, which is 2, close it off, and then plus the D value, which is 5.25. And there we go. There is the equation of just some arbitrary thing that I just drew on the page. This is a relatively challenging exercise to do something like this, because you have to kind of estimate where things are, and you have to have a real command of what's going on. Most of the problems in the textbook will give you enough of these labels as they stand to be able to do this. There are a couple of applications that don't quite do that. You have to kind of put the pieces together to do that, but there's not a whole lot of them. I think that that's something that's far more relevant in a physics class, but you know, maybe just a little stab at it isn't too bad. Okay, so I think that is really the sum of what I want to do for section 4.2. I know it's kind of a short section, but I think when you do the homework, you'll start to see a lot of examples of this. Over the years, I've tried to beef up the number of examples. There just aren't really a whole lot in the textbook, unfortunately, but so be it. All right, well, I will see you guys at next during the segments for section 4.3.